Hi, everyone. Thank you for coming to the seminar today. This is our second seminar, or I guess third-ish seminar of the semester. You might notice that I'm not John. I'm filling in for John today. My name is Kazi. I am Essex Communication Coordinator, and I'll be moderating the seminar today. Our Associate Director, Ralph Ferrer, is also here, and he will be introducing the speaker in just a moment. As a reminder, the seminar is being recorded, and the recording will be published on our YouTube channel, Essex UMD. Our YouTube channel is pretty robust at this point. We were talking about it earlier. I just put a link in the chat if anyone is interested. We have a lot of recordings up there, including last week's, if you missed it. So today we are excited to have our speaker, Courtney Schumacher, joining us from Texas A&M, and I will let Ralph, our Associate Director, introduce her.
Okay, yeah, we're excited to have Courtney here give our seminar today. Anybody who's been involved with a lot of the NASA precip missions, science teams, and so forth, Courtney for a lot of the work she did when she was at the University of Washington. A lot of field campaign work. There's Andy waving his hand. He knows Courtney quite well. And yeah, she's professor at Texas A&M University. Got her degrees. Correct me if I'm wrong, at University of Washington. And she's going to probably give us a really good talk on convective stratiform work. And I think it's going to be using a lot of GPM precipitation radar data. So we'll give it to you, Courtney.
Great. Thank you so much, Ralph.
Yeah.
I will try to have the chat up. Keep it on the side if you have questions as we go along. But if you can hear me and see me okay, I will just get started. Okay, so I'll be talking about one of my favorite things. I see a lot of names I know and people that know about convective and stratiform, rainfall, and then I will be using a lot of the TRIM and GPM radar data. So again, people that are familiar with that, but hopefully I'll give it a different twist. And those of you who aren't as ingrained in that framework, hopefully I'll provide interesting information and insight. Okay, and I should mention a lot of this work has been done in collaboration with Aaron Funk, a research scientist in my group. Okay. This is the topics to be discussed. We'll see, I think I can get through them. I talk quickly, but I will try to be a little bit more, timely as I go. So I'll be looking at, again, the satellite radars from TRIM and GPM, mostly GPM, because I am, lo and behold, I will be going into the extratropics. I'm much more used to the tropics, but I do want to extend into the extratropics some of these frameworks. I'll be talking about convective and stratiform rain types, things about their distribution, the rainfall contributions, diurnal cycle, et cetera. There's a number of paradigms that I'll be talking about, things like trimodal convection, shallow deep to deep transition. Those are basically convective phenomenon, whereas the next three, stretch building blocks, MCS structure, mesoscale rain bands, those contain significant stratiform components. I'll be showcasing a new paradigm. I think that's a very interesting one to compare storms across the globe using convective and stratiform rain types and the implications for that for rain area and heating and things like that. Also, that'll be probably like 2/3 of the talk, and the last third or so, I will go into how GCMs, they're not going to get these exact rain types that are observed by radar, these fine scale storm types, but they can, what do their different rain types mean and look like and do in the same sense in terms of vertical structure and diurnal cycle and such. And my overarching goal is I really want to highlight the importance of these global rainfall types in both from physical and modeling perspective. I see Ralph has put a chat in there, something about Andy in his past. Yes, and the convective stratiform technique, a great one, using the infrared and microwave, or just infrared. Okay, so this is what you get from text. You go into a 201 textbook, and I'm sorry, I'm getting my chat cleared up here. And you think, these are the different rain types, these are different clouds, and not many of them rain. And right here I have just two types, nimbostratus and cumulonimbus, circled. So allow me to add two more. this is my class always laughs at how bad I am at drawing on the board, but I'm also quite bad at graphics. But this is the best I could do with this textbook picture. But it's not just the nimbostratus at the low levels and the cumulonimbus, but we also have congestus. So once that gets to a certain depth, that's going to have rain as well. And then of course, oh yeah, thank you, Andy. It's just IR. At any rate, so see, I told you I would be checking the chat. But at any rate, and then we have this nimbostratus that's actually a mid-level cloud that also rains. And often I'll be talking about connected to deep convection. And I will be going over this throughout the talk, but the vertical motions and microphysical growth processes are very different in these cloud types. And so that really does already warrant their separation. Not all precipitation is created the same way. So now we get pretty pictures. This is what the convective and stratiform rain types look like from the GPM DPR. For those of you who are not as familiar with the DPR, it's the second spaceborne precipitation radar. The first one is the TRIM PR. I'll be showing a little bit of that, but more I did want to focus on the DPR. It's got a dual frequency KU, KA band. It's similar to the PR that it has a 5-kilometer footprint, 200 at meter, 250 meter vertical resolution. It's got a better sensitivity, about 14 dBz. And then the swath width is similar to TRIM after the boost, 245 kilometers. So these are a couple different pictures of what, for example, the congestus or shallow convection would look like. This is over the coastal Brazil. This is the horizontal cross section, and then across the swath, here's the vertical cross section. It's shallow because the ecotops are below the 0 degrees Celsius level, which is about 4 to 5 kilometers in the tropics. Here you have deep convective rain, a much bigger system with heavier rain rates. And here you can see deeper convection, some tops going up to 14 kilometers. Here is strong rain at the surface. Here's our stratiform region with bright band, again, near that 0 degrees Celsius level. I did want to differentiate too here. There's a kind of its own standalone convective cell here, but it also has little side bits here that are shallow as well, but those are called shallow non-isolated. And I'll use those a little bit throughout the talk, whereas here, these are just shallow isolated because they're not connected to deeper convection. And then this is where those of you who know me are going to be like, oh, wow, Courtney's showing an extratropical. This is a cross section through an extratropical cyclone off the coast of Japan. It was soon after GPM was launched. And you can see just from here, it kind of doesn't look too different than this is also over Brazil, this middle one, it's sort of central Brazil. But then when you take the vertical cross section, you can see the bright band can get quite low. The 0 degrees Celsius is much lower as you go further north, and then it kind of increases in height as you go further south. These rain types are defined by radar-based texture and heights. And so if you want any more details on this, you can ask me now or later. And then I want to note that the ecotop height is not, I will be talking about ecotop heights. It's not the cloud top height because of the sensitivity of the DPR. It's closer in deep convection, but when you start getting into stratiform regions and really small hydrometeors, there'll be a lot of cloud aloft that the DPR might not see. Okay, so this is the view before GPM was launched. And so this is, I've done myself, my group, a lot of other people in this community have done work with what we've seen from the TRIM PR. And here, these are these 3 different rain types, the shallow isolated, so not connected to deep convection, and then the deep convection and the shallow stuff connected to it. And the stratiform rain, this is just the coverage. So shallow convection on the order of 1% in the trade wind region, stratiform 6 to 8% over the ITCZ regions and continents, maritime continent and others. And these look, the deep convective and stratiform look, they're coincident in their maps. They look a lot like, if you had put up a rain map, they'd look a lot like the overall rain map in the tropics. And so that's a great view. But I do want to point out the TRIM satellite only went from 35 north to 35 south. That's in the yellow here. And that was up for a long time. So we have a really nice data set from that. But we also now, GPM was launched in 2014. So we have now we have this incredibly long data set, decades of observations across the globe with these spaceborne radars. And again, both of them have these KU radars capable of observing convection and and especially the diurnal cycle because of the precessing orbit. But GPM, I'm going to flip now. This is going to be a little bit like Dorothy going to Kansas. No, from Kansas to Oz. It's in color now. It's to higher latitude. So this is what the GPM rain types look like. This is 8 years. So since the launch, this is the new version 7. And I'm going to be showing this pictures a lot. You're going to kind of maybe get tired of them, but I hope not too tired of them. And so in this case, we've reorganized things. We've just put everything all shallow. So shallow, isolated, and non-isolated go into this top. So that's why we get on the order of a couple more percent, just in terms of coverage. And they're really focused, this coverage of this rain type is really mostly over the oceans, the tropical oceans. When you go to deep convection, and so here, this is anything that's not the shallow or warm-topped convection. I'll get to that in a second. Again, you see something very similar to what we see from TRIM in the tropics, but then we do get occurrences, less than 1% in the extratropics. Stratiform rain makes the biggest change into the extratropics. So we have our typical tropical pattern, but then we get even more, much more stratiform occurrence at the higher latitudes. And then so again, we're going to be going over these different rain types and their locations throughout the talk. So I'm going to just keep on going. So now I just want to focus on the ecotop distribution that goes with each of these. This is by latitude. Again, this is ecotop, not the exact cloud top height. And so this is where you can see that all the shallow convection that we've grouped in here, it's just warm. So it's where the 0 degrees Celsius is, it's below that. Whereas the others, the deep convection can extend up. This is cut off at 2%. So there are even higher tops. But the deep convection can get 16, 18, 20 kilometers in the tropics. The stratiform can also get quite high, 12, 14, 16 kilometers. And then it drops off because that's the tropopause is getting lower. It's also, things like the 0 degrees Celsius level is getting lower as you go into higher latitudes. So that drops off. And so that's when I'm talking about the deep tropics, I'll probably stick with shallow and deep convection as my names. But when we go into the full global view of these rain types, we're going to separate things by warm top convection and cold top convection. So this is cold topped. I wouldn't call it deep, but it's certainly still likely cold tops. Okay. So now I'm going to squeeze back into a tropical view of things. So I kind of blanked out the higher latitude. So we're back to shallow and deep convection. And then I'm going to first start with the first paradigm I want to look at. The trimodal convection. People know this is a very famous paper by Johnson et al. From 1999. And they used ground radar data and other data sets, especially from the West Pacific, to draw this view of how all three types, so non-precipitating shallow convection, precipitating shallow convection, so the cumulus here, and then the congestus here, and then the really deep cumulonimbus, where they are, they're all three important to the tropics, especially in this geographical view, so the spatial view. And so here, this is very consistent. These two towers are very consistent with where Dick Johnson and others put these branches of the upward branches of the Hadley cell. But I wanted to point out with this global view, we're not just left with what we see in the West Pacific, but we actually see this sort of more global view. And we can see that really it's this northern branch that's more important to this geographical version of the trimodal, especially in the Atlantic. The Atlantic and the Pacific. Here in the Indian Ocean, though, it sort of straddles the equator. It's a smaller basin, you don't have a cold tongue. And so that where this is, this paradigm is really dependent on where that deep convection is strongest, is really dependent on what basin you're in. Okay, and now I go to the next one. Sorry, I don't have as many bullets as I maybe normally do, but I think I have a lot of pictures and annotations to help along the story. Now the congestus part, so the shallow convection, which is the raining congestus part. Here you kind of get 3 points where you get congestus on either side of the deep convection, and then you have the congestus sort of in the middle, or that coincides with the deep convection. And again, that's really consistent in the West Pacific. But again, as you go, I've just overplaced these same boxes that I had for the deep convection. You can see that, again, here, the trimodal this trimodal view where congestus is also a very important type varies on the basin. So here it's, I would say the southern hemisphere is much more important for that trimodal, and it's a little farther south than what this diagram would have. Whereas, you know, the Indian Ocean, again, it's more focused on the southern side because you have land to the north. And it's, the other thing I want to point out is there's not a lot of congestus over land. So this trimodal convection is really much more of an ocean paradigm. Sometimes people do invoke it over land. I should point out, there is a little more congestus over land than this DPR climatology would maybe have you believe, because we're capping things off at about the 0 degrees Celsius level. I wanted to point out Christy Wall and others used infrared data and CloudSat data together to look at tops that were more like 5 to 7 kilometers, so they're like a sort of deeper congestus level. And I just saw George's question, so let me go back to that in a second. And there's a little bit more relatively over land, but still I would call this, I would say that's, those aren't strongly congestus regimes over land. Okay, George asked, the Indian Ocean and Maritime Continent have considerable cross-equatorial flow that varies by season. I think this is why the picture in those regions is different. Oh, absolutely. So that's a great point. So seasons would be a really good way to look at this. So, oh, thanks, George. This is excellent. So I'm just throwing out here, these are paradigms that I feel like need to be assessed more with the DPR data. I haven't done this. I'm doing a pretty broad overview of a number of different paradigms. And so I think exactly looking at things seasonally or different timescales would be really important to kind of highlight what when this paradigm is applicable, when it is most useful, and when we can't invoke it. So what I think is actually over land, so I'm now switching over to land. I'm going to very briefly talk about the shallow to deep transition. I think when people talk about these different convective cloud, these just convective only cloud types, I think it's more interesting to talk about in time over land, the diurnal cycle. Yeah, I thought I had that. So on the top is the counts. It's just the counts of each type. So I do have the shallow isolated, the shallow non-isolated, and then the deep convective. So there's 2 different types of shallows. And mostly, again, over land, most of it's deep. And there's less of the shallow because it's transient, right? It's growing rapidly over warming land into the deep convection. But when you take the hourly anomaly, I think it's a little more interesting. Whereas there, you cannot start looking at the transition because, again, we have that precessing orbit. We can see the change in the diurnal cycle of these different types. You can see that it's the shallow isolated that kicks off early before noon in an anomaly sense. And then you get your shallow non-isolated. And so things are starting to grow and deepen. And then it's really not until about 5 or 6 o'clock in the afternoon, evening, that you get the deep convection maximizing. And so the shallow to deep transition, again, so I think that's a better paradigm to use over land where the congestus is more transient. And then the trimodal is a better ocean one. Okay. Let's go to our next. I'm zooming through paradigms because there's lots of things I want to talk about. By the way, on the left, I'm popping things up that are important. So now I'm going, and the title of the slide should help you say, now I'm looking at all types. So before I was just focusing on the convective types. And so now I've gone back and I've added stratiform in. It's not that stratiform rain. Stratiform rain is very important in the tropics. And here I really like this paradigm. It's the stretch building blocks, where there's this idea over scales from MCSs, so mesoscale convective systems, to 2-day waves, to Kelvin waves, which are more like 4 to 5 day events, to the MJO when we're talking many weeks. So this intraseasonal oscillation. So this idea of that the relative importance of each of these types are extremely important to these synoptic scale and longer events that cause a lot of rain in the tropics. Again, I want to point out, because if you want to say that shallow convection or the congestus category is important to these, it really is, again, more of an ocean phenomenon. But that anywhere where, again, it's rainy, each of these rain types are important that you can kind of delve into that a little more with the DPR data. And again, I think there's certain places over land that these apply, but not nearly as well as over the ocean. So again, I'm going to call this more of an ocean and tropical phenomenon, because again, that congestus category really you don't go it doesn't extend deeply into the extratropics. Okay, so something about the stretch building blocks that's cool. So just to go back, oh yeah, so this is still Mapes et al. If you just look at the different impacts, this is divergence, although I think this is heating that I'm adding in, or just the cloud, the cloud occurrence or humidity. No, I've forgotten what I put here. I wanted to point out that the shallow clouds, it's the precipitating ones that matter. The shallow ones are the ones that don't precipitate are tiny. They're, a kilometer. Once you get to about 1.5 kilometers or 2 kilometers, you're precipitating, especially over the ocean. So this part of the stretch building blocks is really it's what we see with the DPR and PR. Because yeah, this is the kind of moisture impact that we'd expect from the shallow clouds. Now I'm going to kind of highlight the deep convective part and the stratiform part, which again are highlighted here by these two regimes that are overlapping, highly coincident in the tropics. And so this is a mature MCS. That part of the building block is sort of the same kind of dynamics and microphysics we'd expect in the convective and stratiform region. This is that nimbostratus attached to the deep convection for an MCS. And here you can see this is actually, now I'm putting a little bit more in terms of the vertical motions. We'd expect very strong vertical motions in the deep convection overall, but downdrafts at lower levels where evaporation occurs. In the stratiform region, we get a mesoscale updraft, so lots of small ups and downdrafts that equal out to kind of a weak ascent. And where you have vapor depositional growth here. In the convective region, you have more collisional growth. You have cloud base about the 0 degrees Celsius level and rain below that. So there's a lot of evaporative cooling happening there. But I want to be open-minded. So now this is when I get to expand. Oh, shallow, but I want to say shallow rain is not important to the mature MCS water budget. It might be important in the stretch building block thought, but it's not really important to a mature MCS budget. It's not deep enough to help feed the stratiform region. It's not a big rain producer. And the other thing is, MCSs don't just occur in the tropics. And so this is when we can start saying, well, let's look at what MCSs look like at higher latitudes with the radar, right? The spaceborne radar, instead of just having, a few radars here and there at wherever land location you might be lucky enough to have a good data set at. And so, but there is a lot of rain up here. Is it all from MCSs? No. That requires deep convection, very deep convection. We know not a lot of it's very deep. And so the other paradigm that I kind of want to bring up is mesoscale rain bands. So in these, this is an extratropical cyclone. This paper by Maiteka and all, it gives a great view. It explains all these different types of rain bands and the way they form. But I think it really importantly to say each of these rain band types contains some form of cumulus scale convection. And I've just chosen one. I've just chosen 1A. I've shown this picture. They have the schematics for all these other types. But this generating cells, this idea of convection is, even though most of this is stratiform rain here, we can see most of these extratropical cyclone regions, especially over the water, are stratiform in nature. There's still a convection that goes along with them. So I'm going to flip back and forth. How do we know? Are we in an MCS environment where we have deep convection and nimbostratus forming from that? Are we in a region, more of a situation where we have large scale stratiform uplift, isentropic uplift with some generating cells playing a role? And again, not clearly global, we're not sure exactly the role. And so that's what the DPR can help us understand. Okay, I think I'm done with the old paradigms, and now I'm going to kind of say, well, now how do we decide? How do we choose which type of storm is happening and its impacts, right? Like it's rain, it's heating, it's, its size, all these different things. So I thought, well, this is when this is the time of the peak counts. So I'm taking this occurrence and saying whenever the most counts, that hour it happens. I'm using TRIM and DPR and the GPM radar because just to help with sampling, although there's not much of a change. So I think the DPR, we've had enough years of DPR, so we're getting a pretty good long-term sample here for the diurnal cycle. And so over land and globally, really, you tend to have, I'm going to move my chat box a little bit so I can move this. You over the Amazon, for example, from Andy did a lot of diurnal, excellent diurnal work, and others, Bob, George, others on this list. So we see an early afternoon peak, which is a little bit later over Africa, Central America. But I'll say we tend to get these kind of afternoon peaks over land across the tropics and extratropics. There are some regions where it's a little later, and I'll explain those in a second as we go down to the stratiform regions where you start getting later, you start getting into the blues and greens, blues and purples. And that's when things are evolving. So mesoscale convective systems or extratropical cyclones, whatever it is, but this tends to be over, well, I guess there's a lot of blue over the ocean too. It's not as clear of a signal as the convective. Things evolve later in the storm system. You get more stratiform rain, at least in the MCS categorization. Extratropical cyclones, maybe to some extent, but it's really, we see that this over land much more. And again, it doesn't seem to care if it's at higher latitudes or lower latitudes. We definitely have a later peak from the stratiform. So the timing of the system is really, doesn't seem like it's going to really help us at this moment, just from this simple view of things. But there's a lot going on here, and I'm going to hone in on one region in the Amazon just later on, because there's a lot going on in this map. So I've been talking a lot about occurrence, ecotops. Let's go to rain amounts. So maybe rain amounts helps us out somehow. And so now I've put all the rain types up again because they all contribute to the rain globally. Here's an annual rainfall map from the DPR. And then if you break that down by type, sorry, I just moved my chat box. If you break that down latitudinally by type, you can see that the red line is all convection. So we have most of our rain, the majority of our rain in the tropics is convective, although the stratiform is blue. So this is a little higher. This is about a 45% of the rain in this kind of tropical region is considered stratiform by the DPR. It's a little bit higher. Previously, we had said 35, 40% in some of my group's previous work. But still, it's still majority convective, although about 10% of that is this warm-topped or shallow convection. And then the rest, the sort of cold-topped and stratiform rain is pretty equivalent in the tropics, so they're equally important. So again, yet another reason to look at different rain types. And then once you start, the nice thing now that we've got the DPR, we can say, well, around 25 north and south, stratiform rain starts really picking up and becomes really the predominant rain type. And then if you look at actually maps of the percentages of that, this is what it looks like. I think it's a beautiful view. Aaron put it together, really nice color scale on this. So it's not a linear scale, but he picked different percentiles of the values just so we can get kind of a regime view of things. So here where you have these blue colors, these are very low stratiform rain regimes. So these are sort of going to be the low rain regions. Here we're in the trade winds and things like that, and cold SST regions where we're not going to have a lot of rain, but it's definitely not deep convective. It won't form stratiform rain very easily. Then the next level up is this sort of these kind of red to orange colors, where we tend to have this is where we have our MCSs and the Kelvin waves and the MJO and things like that. This is where they're most active, and a lot of MCSs. And so this is certainly where we're getting about half and half of the rain is stratiform versus convective. Then you kind of rapidly transition in the subtropics to this very highly stratiform regime. And so this is where we're getting 70, 80, 90% of the rain is stratiform. And that can vary a little bit over land and ocean. And there's some regions over land that seem to kind of pop out a little bit and be not quite as high as stratiform rain fraction. And that is because, we'll come to that, it's now the seasonal variation. So this is good. We're getting a little closer. We're sort of like, okay, some comparison of stratiform and convective rain is helping us determine where these sort of regimes go. But here it breaks down a little bit. So if you look at the seasonal stratiform rain fraction, then in June, July, August, which is the top panel, this is when you tend to have that more MCS, or I would call it a tropical kind of regime where things, you know, I mean, this happens over Europe and Asia as well, where we tend to have more MCSs, not only MCS. So I think like Fung et al. Have a really great paper out about the MCSs, the seasonal MCS distribution. And it's not the same. So not all the rain is coming from MCSs here in this warm season in the Northern Hemisphere, but certainly there's a strong seasonal variation in the, oh, I have this, in that, because then you look at December, January, February, and that goes down. So in December, January, February, it becomes a very highly stratiform regime. So you can't just break things down by latitude. You can't say you hit 35 north and it's extratropical above that, or 40 north and it's extratropical above that, and it's tropical, you know, equator of that. You just can't do that, because certainly, especially over land, you get this flip flop. It happens over all land regions, including Australia. So this is me going, I hope everyone appreciates this, especially people that know me, me going into the extratropics. I'm going to go even further into the extratropics here. And I'm going to talk about the North Atlantic. And so that's an interesting shift too. We're going from actually the most stratiform regime we have is in June, July, August, so the warm season in the North Atlantic. And you actually become more kind of convective. So you kind of get these more darker greens. So there's kind of convection is becoming more important over the over the North Atlantic during the local code season. And I'm going to give one example of that. Again, I'm teaching a tropical meteorology undergraduate class, and I told them, oh, I'm going to show something from the Labrador Sea. And they're like, no, really? And I was like, yeah, I'm going to show a picture. So here is, this is MODIS with some MERA data overlain on it. This is marine cold air outbreaks. So when you have the cold ocean surface and warm air coming from land coming over it, that's creating an environment where you can have a lot. This swath right here is the DPR, and so you can actually see a lot of convective elements in that in this region. And then I included the cross section there, so you can see very shallow but still, you know, evident cross convective cells. I want to show that there's this cross section is also along a CloudSat nadir curtain view. And so you can see that the DPR does have issues at the swath edge about how low it can go. And so if you do want to do statistics at higher latitudes, especially when you're looking at very low convection, I would definitely recommend looking kind of on the inner part of the swath. You get better statistics. But I did include, just for full disclosure, that this is what the CloudSat looks like. Again, they're overlapped. This is here where they're overlapping. And CloudSat sees these convective elements. CloudSat also sees a lot more cloud above. So our DPR is simply not sensitive enough to see that. But the precipitation size particles it'll see, the precipitating part of the storms, it can see. So that's kind of exciting. Okay, so I like this. Of course, I'm going to like the stratiform rain fraction framework. It's something I've been working on since I was a graduate student, working with term data. But now I'm going to go back to, well, what else? I think there's maybe what other ways can we look at those two different types of storms, right? The deep convective stratiform storm versus the kind of large scale uplift with some embedded generating cells in the convective in the convection. And so here, I showed these before. These are the echo top distributions for stratiform and cold top convection. And if you subtract one from the other, you get something that looks like this. And so again, this is saying, well, here's where convection is dominant. Deep convection is dominant here. That's just where we get more of the tops. They're taller tops. And then definitely stratiform rain starts again becoming more predominant somewhere in some region here that might have seasonal variations, kind of like George brought up before. Seasonal variations can be important. And so here I would definitely say this is a stratiform dominant regime. There's a lot more stratiform rain. It's taller tops, so it's not gonna be convection feeding stratiform rain, right? It's more of the stratiform rain. It's dominating both the number and tops. But then, you know, in some region in between. So yeah, how do we clean that up a little bit? So this is where now I get to introduce this new paradigm. I'm just taking this map, the convective and stratiform, just the 1 degree average. This is the grid average of each one for the year annual mean we have. And it's going to be the stratiform occurrence and the deep convective occurrence, or that cold top convective occurrence. And look how clean. I mean, I was just sort of shocked when I saw how clean this came out when Aaron provided this. And so you can say there's really two populations. There's this population here where we have low, deep, kind of cold top convective occurrence and kind of large stratiform occurrence. And here where you have more of both, or you have the same stratiform occurrence, but then more deep cold top occurrence. And they're so tightly grouped. And so if you take that ratio, if you take these lines, you can say, well, here this is saying 22% of whatever of that grid is covered by convective rain, and the rest is stratiform. Whereas here it's a much lower number. You only have about 5 or 6% of the area covered by convective area. But it's so clean, right? It's so crisp. It's sort of like saying, how much rain convection do you need to create a big stratiform area? And it depends on partly where you are. So when you take these same grids and you say, where are those grids in latitude? So this is the mean absolute latitude. It really follows exactly what you would think. On this bottom line, this bottom population, it's all the things that are poleward of about 30 or so, 30 to 40. And here, these are things that are equatorward of that. And so it's really highly location dependent. And then also, it also speaks to how much rain can be produced by each of these systems. So this is the conditional rain rate. So in that grid, it's saying if you have this average stratiform and convective area in that grid, these are the typical rain amounts you would get for the year. And these, again, they're very different. They don't really change that much along this lower curve, this, so you're at about 1 or 2 millimeters per day, no matter what. So it doesn't matter kind of how much area you cover. It's just how much that's just how much rain where you're producing. Whereas when you get into this regime where convection is more active, it's more important, you start getting much higher rain amounts. And so even for the same stratiform rain area or occurrence, I'm using them interchangeably here, you're getting much lower rain rates in this regime versus much higher ones in this regime. And so that's, this is really clean and it's nice. And you're kind of like, well, how good is that? But I should point out too, you need some convection. So you can't just have a bunch of stratiform rain without convection. So convection is sort of, at some extent, you have to have a little bit of it. So we know those generating cells are important, but they're just not driving maybe the area and rain amounts as much as in the kind of more active convective regime. And so you might say, well, these are just grid averages over 8 years. How relevant are those? And so here I am showing the orbital distributions of for just 4 grid boxes. So 2 high latitude grid boxes, one over land, one over ocean. Here, 2 tropical ones. And the ones over the higher latitude ones are these 2 colored ones, the kind of red and blue. And here, even on the orbital scale, you're getting very high numbers. That's that ratio, this 5% versus the 20%. Here you're getting so this is saying on an orbit-to-orbit basis, that's a statistic that sticks, that you need a little bit of convection for these things to keep on going. It's a little less clear in the tropical cases. You get more flat lines, but you still do get most of your, the majority of your occurrences greater than about 10 or 15%, which is consistent with work, current work or recent work by Greg and others on the importance of needing at least a certain amount of convective rain to maintain a large stratiform region, at least in the tropics. Okay, maybe I'll take 5 or 10 more minutes to talk about how this applies to GCM rainfall. Yeah. And what does rain types even mean? And so I have more than I can say, so I'll just skip to maybe some of the most relevant ones. Here, this is just, we all know that the GCMs are kind of imperfect in their rainfall production. It's a hard thing to even measure, and much less analyze through large scale grid variables. But there's a lot of problems that they are persistent across all the CMIP versions, at least in recent memory. Things like too much light rain and not enough heavy rain. So that's this drizzle problem. Diurnal biases, so rain that's too early. And then geographical biases like the double ITCZ or an overly dry Amazon. And of course, the way that you just have these grid scale like temperature and humidity And the way that you can get rain from these GCMs is from either the convective parameterization, which is assuming some distribution inside the grid, which can either be deep in rain, or the shallow rain typically doesn't. I mean, the shallow clouds typically don't rain. Or the large scale here, I don't have a picture of it, but otherwise if there's not enough rain produced through the convective parameterization, then the large scale microphysics, just the whole grid just rains, right, at a certain point, if the convective rain hasn't produced enough rain. So here, let's see what a couple models look like. People have done this. Dai et al. He's been very good about going through the different CMIPs and saying, well, this is what we get from the spaceborne radar. We know this picture I've already shown. But here, this is just, I grabbed one CAM5, or Aaron grabbed it using some awesome Python code. And he's kind of using pretty much kind of a similar color scale to slight variations on it, just based on the distribution of stratiform. Of large scale rain in CAM6. And I don't know, when you first look at this, you're like, oh, this is cool. Like this is pretty good. I can handle it. It's maybe not perfect. They're getting a little bit too much blues, like too much high convective here. And maybe, oh, I wanted to put that much stratiform rain in the Labrador Sea, whatever. But I don't know that. I look at this and I'm like, oh, this is great. Then he went and grabbed, I'm going to hone in on the Amazon. So Aaron went and grabbed just 4 other random models. Again, this is sort of many, a couple decades of averages of the large scale rain fraction. And they vary quite a bit depending on the model. And then when I bring up kind of what I just mapped in the same color scale, this is what TRIM and GPM, our long-term climatology looks like. I don't know, you could say, well, which one is your favorite? Well, it's not really that. I don't think you should do that because these are not comparing the same things. Convective rain and large scale rain in a GCM is not the same thing as what a convective and stratiform rain is observed by radar, but we do still want to see patterns like here, when you have high large scale rain fraction over the Amazon, you'd also want to see it over the ITCZ. Or you want to see probably more large scale rain, or is it all being done by convection? Then this parameterization has to do the work of both the convective and the stratiform rain. And so what work do I mean? Oh, I had to highlight this because this is work by Steve and others that have shown that how much rain comes from MCSs or mesoscale convective systems. It's a lot, and this stratiform rain fraction is highly correlated to that. So this is just, kind of saying, oh, this is a good metric in general for storms and storm organization. Okay, so what do we care about when we talk about impacts of the rain? So it rains, but it's not just the rain, it's the heating. Oh, it's the heating associated with the rain. I'm making a decision now about what I want to share you. Let's see, because I just have a few more minutes because I do want time for questions. I know, I'm so sorry. I was going to show all this stuff from the Amazon and from West Africa and from machine learning. But I think I'm just going to go to the US for the sake of time. So what we care about is things like the vertical structure of the storms creating the rain, because of things like the heating or the vertical motion associated with them. We care about getting things like the timing right, like the diurnal cycle right, because we want our storms in the right place at the right time, looking about the same way they should. So I just need to briefly show the way that GPM can be used to evaluate models in the vertical kind of unique way. This is work again by Emily Riley Della Ripper led this work for my group. But taking things like a COSP simulator, which is typically visible infrared, even CloudSat, so cloud radar, output from just sort of those cloud variables from GCMs, and then put them through a simulator and say, I'm going to input these variables and then output reflectivity, which is what the radar sees, because it's hard to go from reflectivity to these other variables. And so we can do that, and we can use CFADs to compare these. These are contoured frequency by altitude diagrams. So we've spit out this, in this case, we're using CAM5 data. and different latitudes. So the tropics here are in the middle, the GPM is on the top, the radar, and then the CAM5 is on the bottom, and then these are higher latitudes on either side. And so the CFAD just gets rid of any XY components. You're just looking at the vertical, so you have reflectivity and the vertical, what that distribution looks like by height. And so you can see in the tropics, you have deeper convection, deeper echo, deeper reflectivity, deeper storms, and higher reflectivities near the surface, so more rain. Whereas here, like in the northern hemisphere, we tend to get storms that are higher than in the southern hemisphere because we have our land storms here, kind of US and Asia and Africa and Europe. And CAM does okay in this. This is 2 degree, but we've done this with 1 degree as well. So it's not perfect, but we're saying, well, kind of getting some of the same ideas of more higher reflectivity at lower levels, and then these sort of heights that are looking realistic, not as perfect as we would like. And so then we did this, we said, well, let's look over CONUS. Let's look at the CFADs in a few different ways by rain type. So I'm just taking June 2027, 27, looking at the clock. June 2017, and so this is the precipitation observed from NOAA. And so here, this is the anomaly for that month. It was a little wetter. It was a normal month pretty much, except here is a little wetter because tropical storm Cindy came along, and this is the anomaly from that. So if you look at CAM5 from this month, it's just forced by SST. So you're not expecting an exact storm by storm match, but the CAM5 rainfall total but you're still expecting at least the same kind of spatial scale over a month, same type of storms expected in June. Oops. And you can see that CAM5 has too much rain to the north. It actually gets this. I don't know if the SSTs like it got Cindy or not, I'm not sure. But when most of that rain is not convective, is actually large scale. So most of this rain, even though this is June, we expect a lot of that rain to be convective. A lot of that CAM5 is producing that rain as large scale, and especially the offset, the spatial offset is from that is from the large scale rain. And even if you consider this to be some lucky capturing of Tropical Storm Cindy, it's still through the large scale, not from the convective parameterization. And then finally, this is gonna be my last picture. It's a lot, but this is why I had to introduce CFADs and the simulator. So if you separate the CAM5 reflectivity into convective and large scale, it's looking a fair bit different. There's some similarities, but there's a lot of differences as well between what the DPR sees. Again, this is a longer term climatology just for June. Over CONUS, over the US. And so the convective, at least if you just compare the convective CFADs, I'm not unhappy with CAM5. It's too weak in comparison to reflective, but maybe that could be part of the way the simulator works. But at least there's vertical continuity. This looks like a reasonable storm to me. I would like it to be further over in terms of the reflectivity distribution, but okay. This is what stratiform CFADs look like. So we have our bright band, our kind of weaker depositional growth processes here, and then lots of rain underneath the cloud base. And again, it's not exactly what I would like. We get even our much stronger rain rates are actually near, and low level reflectivities are in the large scale. So this is just being created by grid scale processes. And then again, we're much too weak. That this ice region is not what I expect from a radar distribution. And then when you look at the peak hour, so we can give the peak hour of these CFADs. The DPR sees, as we'd expect, things the convective. Most of this is over daytime, and then the deeper stuff happens later in the day. So as your convection deepens in the DPR, it happens later in the day. The stratiform is going to be even later. It's going to evolve from the deep convection, and so it's later, tends to be later than the convective region. Whereas CAM5, just it all goes at once. Mostly, it's all just like midday, which we know is just a problem. And then the large scale rain just happens at night. It's just like a totally different time. And this is something we see a lot where the large scale rain happens at a totally different. So in this case, it's shown in a totally different part of the US. It's got a different reflectivity distribution we would expect after the conversion in the simulator, and it's just happening at a totally different time of day. So this speaks to the idea that models, especially GCMs, has to pay attention to these rain types and how they interact. They should be better linked both in space and in time, and even in their vertical structure. So all of those should be better linked. Okay, so there we go. I should have about 10 minutes now for questions. I'll put my conclusions up, but just briefly, hopefully these mostly DPR maps of these convective and stratiform rain types linked to the different paradigms have been interesting to you. I've gotten you thinking, I've gotten you to think about how you can apply these paradigms in more interesting ways. I have this new paradigm where I think it's a very crisp. I was really shocked about how crisp this ratio between the convective and stratiform areas, the cold convection, really delineates these storm types, the kind of more convective versus more stratiform driven storms across the globe. And then of course, I don't expect a GCM to get these storm scale processes exactly right, or even, I mean, I would hope though that it could approximate better things like the timing, the location, and the vertical structure of these storm types, and that it seems like they're acting totally separate, and that they can't be in the real world. They have to at least be interacting. Okay, and with that, I am done.
Thank you. If anyone has any questions, now is the time. You can unmute yourself and ask it, or you can put it in the chat and we will address it. Oh, I do see a hand raised. I cannot find you. So if you have your hand raised, you can just go ahead and unmute yourself.
I'm sorry, Courtney is Wei.
Hi, Wei, how are you?
Hi, Courtney, so nice to hear and see you here. So excited. Yeah, the topic is so interesting. Yeah, so I just have a question about the cloud top versus the echo top. So we know that a part of cloud top will be missed observing by the tree precipitation radar due to its low sensitivity to the smaller cloud hydrometers. But how about the GCM precipitation radar? Does that has a similar statistics like a twin precipitation radar?
Oh yeah, that's a great, yeah, this was a lot more work than we thought it would be. We struggled a lot with this. So yeah, we cut it off to be similar. You're right, but the GCM certainly sees much lower reflectivities here, but we cut those off. I'm sorry, here, this is the GCM. So here, we cut those off. So GPM can't go down that far. We have to cut them off. And it's just, yeah, so the GCM and partly, the simulator itself. So Quick Beam is part of the simulator here that you can actually dictate the frequency and things like that. So that does help with making sure we're not seeing really small reflectivities that are unrealistically small for precipitation radars. Mm-hmm. Yeah, but yeah, you do have to be careful about that. You're not including those lower reflectivities for sure.
Thank you so much.
Good to hear from you.
Any other questions? You can go ahead and unmute. Oh, another hand. I don't know why I can't see the hands. Oh, it's Chip. Chip, go ahead and ask.
Yeah, I'm good for a question. I guess in like a sort of a lifetime of the convective elements, lifetime of the cloud, if you want to say that. Do you have a sense in like, I guess I'm thinking about like the oceanic tropical deep convection. What percentage of oceanic tropical deep convection doesn't go on to develop a to feed into a stratiform? I tend to look at like field campaign data, so pretty much all of them it seems, but that's because they're all looking at, the tropical disturbances and stuff where that feels more common.
Yeah, it happens a lot. No, that's a great question. There's been a lot of people, there's a lot of work done on transient versus, the ones that kind of stay a fair bit. So this is exactly why this population looks the way it does. There's a lot, and then if you go out, I don't know if you've spent time in the field, and you're not just chasing tropical cyclones, but if you're just sitting around, like on a ship, like or in Kwajalein or something like that, a lot of times you'll just look around and you'll just see congestus. I mean, there's lots of fair weather cumulus everywhere, right? That's ubiquitous, but there's stuff, it just never gets that deep, and it just kind of hangs out. And then occasionally maybe one or two really deep ones hang out, but you definitely. They definitely are more terminal. Yeah, there's a fair, like, this is exactly why this distribution looks the way it does. Whereas over land, it happens, of course, it goes through that stage, but it quickly deepens. So it's, I think it's by day too. It's sort of, that's where that stretch building block comes in, where it's like you kind of have more congestus, and then maybe a day later, you have more deep, right? So it's sort of a slower, the moisture advection that's being drawn in by these sort of more shallow, not totally deep clouds, that can help. And the moistening from some of this congestus can also help further deep convection develop. So that's a great question, but yeah.
Thanks.
Bob, you can go ahead and ask your question too.
Hi, Courtney. How are you doing?
Hi, Bob. It's great to see you.
You showed a lot of variations of convective stratiform under different conditions, geography, blah, blah, blah. How about ENSO?
Yeah, I know you've done some awesome work on ENSO with rain. All your beautiful. Yeah, so we haven't looked at it with the fully extended data set, but I know work I did with TRIM, the PR a long time ago, shows definitely enhanced Pacific stratiform rain production. So definitely, yeah, more of it. And then that affects the heating. So I didn't get to go into the heating as much or at all, but that'll elevate your heating, and that'll change your whole Walker circulation, things like that. So that's a great question. Now looking at this extended data set, I think we'd have enough observations now to say something about more of the global patterns. And especially I'd be interested in looking in the central, and the Modoki versus the more canonical East Pacific ENSO too.
Yeah, and the ENSO may affect us, but maybe not. But if we now have 20 plus years of TRIM and GPM, so at least for the tropics, do you have any indication that there are any trends, like a convective portion or anything like that?
Again, something we've been hesitant to look at, but I think that's a great next step. I think also there's been a lot of work to give kudos to the PMM team about all the algorithm development that's gone on to make things as consistent as possible. So now I think now is when it'd be most possible, because version 7 has come out, both version 7 for GPM, but also going back and doing the TRIM data historically with the same algorithm, I think, and really taking into account the sensitivity changes and things like that. I think if we can do it, we can do it now, but I wouldn't have been comfortable doing it until now. So Aaron and I will work on that and send you the first results. How about that?
Yeah, we're looking at some things from a mean rain rate standpoint, and some things about intensity, and it's a little tricky because of the short time, but interesting.
Yeah, no, man, thanks for those questions. Yeah, speaking of satellites, I was going to end with this. Looking forward, I'm just throwing that up there. Things to be excited about going forward. That we have this amazing data set of decades of vertical reflectivity distributions, but coming up soon will be the vertical motions in both INCUS and EOS. So certainly stay tuned for that. And I think that'll add to these paradigms and our understanding of them greatly.
Thank you. Do we have any other questions? I'm going to lower your hand, Bob, if that's okay. Jackson, go ahead.
Well, hello. Yep. Hey, Courtney.
Jackson.
Yeah. Okay. Question on your Chem 5 results.
Yeah.
So if I understand correctly, what you are doing is you are looking, so when you say convective and stratiform for Chem 5, is that a separation from the simulator, or do you just use the parameterized
large
process?
scale? Yeah, so great question. So we went into this thinking we could do our own separation to make it more like the radar separation. Oh God, it was too hard. It was just too hard.
Okay.
Yeah, so no, it's a great question in terms of like large. Yeah, we're just saying large scale.
Okay.
So
Because that was sort of my follow-up question, which is, could we do a better job separating convective and stratiform from the simulator? But I think
we banged our head on this. I think it's, and we talked a lot about this. I think it's possible, but it would take a lot of effort, actually. But I think it's, I would like, maybe that could be a future thing if this simulator starts getting used. It's really a new product out, so or a new tech.
Because I mean, you can imagine like the idea of convective with parameterized versus stratiform and large scale. I think that pairing is a good first try, but
yeah,
there's something not quite right there.
Yeah, and this is also to go, and I say I don't want people to think that GCM rain is like large scale rain is the same as stratiform. I really don't want it. I want it to be I want it to be considered different, but I still want them to get the same. They still should get the same kind of vertical reflectivity structures in some general sense, and the same heating and the same diurnal cycle. So I don't care what you call it to some extent, but yeah, thanks for that question.
Yeah, right, thanks.
Yeah, Emily, I just saw your chat. So much effort.
Any other questions before we wrap up for the day? Okay. Well, unless someone interrupts me, which you're free to do, I think that we are good to close. Thank you so much for Courtney for giving us this great talk today. This was awesome. And if anyone wants to revisit the talk, or if they missed the beginning, it will be on our YouTube channel, probably by the end of the week. If not, then definitely early next week. And our YouTube channel is ESSEC UMD. It's on all of John's emails if you get those. Well, thank you, everyone. Please join us next week as we continue our seminar series.